Hello, this is at THS Mr. Jones, and we're going to talk about section 5.1. Okay, so 5.1 deals with exponential functions and their graphs. So the first we want to start off with, what is an exponential function? So exponential function is any function in the form f of x equals b to the x. So the main thing here, there's a couple main things. So b has to be bigger than 0, but cannot be 1. Okay. And what really makes anything exponential is this right here. Notice where my variable is. My variable of my function is an exponent. Okay. Just like if we talk about a parabola, what makes a parabola or a quadratic? This square as an exponent makes it a quadratic or a parabola. This x, or this variable, being an exponent makes any function exponential. Okay. Before we talked about parent functions and transformations of parent functions. So this up here is my parent function. So my parent function is f of x equals b to the x, and this capital B just represents my my base number. Okay, it can be any number, but it is my base. So again, this would be my parent transformation function, and we again have our common letters here. So let's just start with the easy one. Let's go with K. So if you remember from the Wheels on the Bus song, K in this equation moves it up and down. Okay. Let's go to A because K and A are related. Okay. So A is a vertical stretch or shrink. Okay. Why are A and K related? Because they're both in the vertical direction. We can go to H. Okay. So H in this equation moves left and right. And if we remember from first semester, it's the opposite of what it looks like. So if it's a negative, it's actually moving right. And if it's a positive, it's moving left. And then the next one is our little b. And that is a horizontal stretch or shrink. Again, same with H, it's the opposite of what you would think it would do. And if it's negative, it flips over Y. So let me add that. So this is negative, and if this one's negative, over Y, and this is over the x-axis. So if the leading one is negative, it flips over the x. If that little b up here is negative, it's over the y. Now we have capital B here. Now, I didn't put that down here, but we can briefly talk about that. Capital B is just your base value. It's kind of like your growth. So if we go back up here to what is exponential, you know what exponential looks like, and it looks like this right here. So this capital B is just the growth rate or the decay rate of this function. So as B gets bigger, this growth rate increases. As it gets smaller, it turns to decay. And in fact, let's note this, that if B is a fraction, or if B is a whole number. Okay, if it is a fraction, we actually have decay, so it's going to look like that. And if it is a whole number or a number that's not a fraction, it's going to look like it's actually growth. It's going to be that exponential curve right there. Okay, that's something pretty important to know. Okay, so we have some pretty specific characteristics about this, and these are just the parent function characteristics. Okay, so let's go over domain. The domain, meaning what x can be, if we kind of look at this graph right here, what x can be, that's going to be all reals. So minus infinity to infinity. The range of my parent function, so up and down, well, it approaches 0 here, but can never actually be 0. So it goes from 0 to positive infinity. Now, of course, this could change. What happens if I shift this down, or if I flip it over the x, or anything like that? That could change. Okay. The x-intercepts. In the parent function, this could be the parent function here. It actually has none. Okay, but again, if I shift this down, this graph down, let's say it looks something like this. Okay, that's still exponential, but now I have my x-intercept. Okay, so initially there is none, but that could change. The y-intercept of my parent function is 0, 1. Let's just look at that real quick. So if I have my parent function, let's just say I have f of x 2 to the x. Well, my y-intercept is when x is 0. Well, 2 to the 0 power is always 1. So anytime you're talking about the parent functions, it will have a y-intercept at 0, 1, no matter what capital B is. Okay, horizontal asymptote is the x-axis. Okay, right here, if we look at this, that's the x-axis. It will come close to it, but never touch it. Another point that the line, or that the curve will pass through, is 1b. That's a capital B. And negative 1, 1 over b. Okay, and these might be important to know, because as we get into this, we're going to be picking points for our graph. So that's a good point to pick. We already talked about if it's a fraction or not, what it does. And it is a one-to-one function. Which is awesome to note, which also tells me it passes the vertical line test, and the horizontal line test. But being a one-to-one function tells me that it has an inverse. Why do I want an inverse? An inverse will allow me to solve this equation for x. Okay, and that's what we're going to do later on. So there are 3 steps to graphing an exponential. Number 1 is solve for f of 0, okay, or graph 0, 1. Okay, so we're looking for that y-intercept. The next thing is find 2 other points. Normally we find points f of 1 and f of minus 1. Okay, again, look right here. Here was f of 0. Here was f of 1 and f of minus 1. So we've got those for the parent functions. And step 3 is connect with smooth curve. Okay. Sometimes I like to pick a few other points, but usually with these 3, you can tell how much your exponential is growing or not, or maybe decaying. Okay. Okay, so we want to look at this graph here, and maybe what happened to the parent function, and give domain and range. Okay, so the first thing we'll say is the parent function. Okay, remember the parent function is b to the x. So my b, my capital B here, if we kind of look at, if we look at this equation here to kind of help us, my capital B is 3. So the parent function is 3 to the x. Okay, so that tells me, since it's a whole number, that it is actually exponential growth of 3. Okay, now we've got the 3 taken care of. We want the plus 1 and the minus 2. The minus 2 says it goes down 2. And the plus 1 means it goes left 1. Okay, so if we start with the original parent function, let's... So the original parent function is 3 to the x. That's going to cross at 0, 1. Okay, if I put 1 in for x, I get 3. And if I put negative x in, I get negative 1/3. Okay, so here's my parent function. Something like that. Again, this never touches the x-axis there. So what am I doing with that parent function? Well, all of these points are going down 2 and left 1. So why don't we just take those 3 points we graphed and go down 2. So we'll go down 2, so 1, 2, and left 1. We'll go down 2, 1, 2, and left 1. We'll go down 2, 1, 2, and left 1. So now my parent function looks something like that. Okay. One thing to note, I had this horizontal asymptote right here. That also gets bumped down 2. So 1, 2. So I do not cross that line right there. Why is that important? For my domain and range. Let's look at domain. Looking at this green line, what can my x values be? They can be anything. Okay. The range. Well, the range is up and down. I moved it down 1, 2 spots. Okay. So how does that affect my range? Well, now I can go down to -2, but I can't choose -2 to infinity. That's why we have the parenthesis there. Okay. That concludes the first section of this video. So here are your 5.1 questions. So go ahead and answer these 3, probably just right after these notes. These are a grade in class. Okay, so make sure you've answered them enough. Here are your suggested problems for 5.1. Again, this one's a challenge problem. The red circle ones are always a challenge problem. If you're going to be in class, you don't need to continue on this video. I'm going to continue through the whole lesson. You're more than welcome to stop watching if you're going to be in class. If you would like to watch, please do. You can go ahead and take this time to like and subscribe the channel and the video and leave a comment if you would like. Okay, moving on with exponential graphs. So we talked about graphing. So let's just do a few more simple examples. Again, this is what I'll be doing in class. So if you don't want to watch, you can go ahead and stop the video. So simple example. Let's just do f of x equals 5 to the x. So if we look at our steps of graphing, the first one we're going to graph is f of 0. So if I plug in 0 here, I get 5 to the 0. Well, anything to the 0 power is 1. So my first ordered pair is 0, 1. Okay. Then we're going to find f of 1 and f of -1. So if I put 1 in there, that's 5 to the first, which is 5. So we're at 1, 5. And if I put -1, that's 5 to the -1, which the negative exponent, remember to get rid of that, we turn it into a fraction, which is 1/5. So it's -1, 1/5. So there's my exponential function. We could do domain and range with this. Domain is all reals. And I can't choose 0, but I can go above for my range. So start from here and go up. Now, again, we can do complex things with this, such as if I have f of x equals, let's see here. Oh, let's just do this one. Let's say 1/2 negative 1/2 x minus 2 plus 1. Okay, so we first want to look at our parent function, okay, which is 1/2 to the x. And because this is a fraction, it's actually decay. Okay, so it's actually going this way. Okay. So we'll look at the other numbers here to see what happens. Okay, so the negative out front flips it over the x-axis. The plus 2 at the end says up 2. And the minus 2 here, remember it's the opposite. It says right 2. Sorry, this is an up 1. Okay, so I would start with each point here. I've got my 3 points here, and I'm doing all of this stuff. Okay, so I'm going to flip it over the x. Flip it over the x. We'll move it up 1 and right 2. Okay, do the same thing. Over the x, up 1, right 2. Okay, so it'll probably look something similar to this. Okay, it will more than likely cross the x-axis somewhere since I'm moving it. So let's just go ahead and check this out on a graph. Again, I'm a little bit off because I estimated some of these numbers, but it comes kind of that direction. Okay, so we need to get exact points, and we'll flip it over and do those movements with it. Domain and range. Okay. I can get my domain and range actually from this calculator. Domain will be all reals. And my range is the only thing changing here. Okay. Well, it starts now, since I flipped it over, it starts at minus infinity. And it looks here like I'm going to maybe 1. If I look on the calculator, maybe going to 1. We can check that on the table. As we keep going up, look at this number right here. Look at those numbers. And we actually end up going to 1. But I know that that is actually a horizontal asymptote. So we're going to put a 1 there because I can't actually choose that. With exponential graphs, we talk about two major things. Okay, we talk about doubling time or half-life. So here's our equation with that. Okay, so we got an equation for double time half-life. P equals P naught 2T over D. Okay, and P is your population. P0 is your initial or your start population. So this one would be ending population, okay, or population after time t. D is your doubling time or your half time. How long does it take to double or to get cut in half? Okay. So let's just say, for example here, so this one's doubling time, this one's half-life. Oh, and T is time. I like half-life a lot because it's used in chemistry quite a bit. So let's just say I have 300 grams of a radioactive substance that takes, let's say, 48 hours for half-life. Okay. Now, what that means is after 48 hours, the amount of substance I have gets cut in half. After 48 hours, the remaining gets cut in half. So we're always cutting something in half. And let's say I want to know how much in I don't even know. Let's just go how much in 10 hours. How much in 10 hours? So we're going to take this 300 grams, and that is, so I want to know ending population. That is my initial population. We're doing half-life, okay? My time will be 10 hours, and my doubling time was the 48 hours, okay? So I just type all that into the calculator here. 300 half parenthesis raised to the, and this needs to be in parentheses too, so 10 over 48. So I actually have 259.66 grams after 10 hours. So we're decreasing, but 48 hours, we need a fraction of that for this doubling time. Okay, so we use double time, half time a lot because I either want to find out one of these times, like how long is the half-life or how long does it take to double. Usually we're dealing with money on that one. Compound interest. Okay. So compound interest is that formula. Okay, so P is your principal. N, and that's also the same thing. That is the number of compounds per year. Okay, T is the time, also in years. R is your interest rate in years. And A is the dollar amount, the ending amount, the end dollar amount. Okay, super simple problems with this. Okay, so real quick, let's just say I invest $5,000 into a savings account. That gets 2.5% yearly, compounded quarterly. Okay, which is what it happens most of the time. So I'm putting $5,000 in for principal, and I want to know after 10 years how much is in there. Okay, so I want to know the ending amount. The principal is $5,000. 1 plus my interest rate is 2.5%. So that's 0.025 over number of compounds per year. There are 4 quarters in a year, so that's a 4. And I have 4 times 10. So N is the number of compounds, which is the 4 again. 10 is the time in years, which is also 10. So I just got to plug this into the calculator. After that's in the calculator, I get 6,415 and 13 cents. Okay. And there's kind of a screenshot of how I put it in the calculator. You can freeze it and take a look at that. Okay. Now, again, what if I know the start and ending amount? Maybe I got $100. How long do I need to get $1,000? How long does it need to sit in there? So we might be solving for one of those two items right there. Okay. Usually we're solving for t, not n. I just accidentally circled it. Okay. We can have continuously compounded interest. Okay. Continually compounded interest. E is a constant. Okay. And it is 2.71828. And it is actually right here on your calculator. Right here. It's the blue button. So you got to hit second ln. It's just a natural number. We won't get into too much detail, but it's the natural base. It's something that occurs in nature, and we use it often to model natural things. Okay. Now, continuously compounded doesn't happen very often, but it is like a savings account that is always paying you. Like every second you're getting interest on it. Okay. Every time they're constantly recalculating the interest on that. Okay. And it works the same way. Okay. This is the principal. This is the rate. This is the time. This is the end amount. And you're just plugging the numbers in. Okay. Again, we will often solve for t. We will get into that later on, actually solving for t, but that's what we're going to use it for. Okay. Again, if you got questions, let me know. These are your suggested problems for 5.1. And then be ready for the quiz. As always, this is at THS Mr. Jones signing off. Thanks for watching.